Welcome to On Ramp, on our way to MBA 643. I am Dr. Danielle Morin, and this is Module 3 on Tables and Graphs for Numerical Data. The program of this module is divided in two parts. We will first look at ordered array and stem and leaf display, and then we'll look at frequency distribution, cumulative distribution, and their graphical representation as histogram, polygon, and ogive. Let us first define what is an ordered array. It is a sequence of data in rank order from the smallest value to the largest value. It allows us to easily identify the range, which is the maximum minus the minimum. It may also help us identify outliers or unusual observations. Let us take an example. Consider the first 20 observations of the data in Module 2 and construct an array for the data on anxiety. This is the data that I need to work from. All what it takes is to put them in increasing order. As you can see, 1 is the minimum, 10 is the maximum, so I can find the range as 10 minus 1, which is 9. Easily done for 20 observations. But if I have several hundred observations, it becomes more difficult. Of course, in Excel, I can use data sorting from smallest to largest, and that will give me the answer. And of course, I would like to expand this realignment so that the other variables move accordingly. And we'll find this. We'd like at this point to show the stem and leaf display. This is a very simple way to see how data is distributed or concentrated. The method is very simple. It does not require a computer. All you have to do first is to sort your observation in increasing order, from the smallest to the largest, of course, and then divide each number into two parts. One part will be the leading digit, which will be called stem, and the trailing digit, which will become the leaf. We'll identify what is more important to know. As an example here, let us construct a stem and leaf display of the age of the 20 randomly selected people who went to see a movie last Saturday. The ages are here. Of course, to build the stem and leaf as we saw, we need to put this in increasing order. And then I look at the numbers that I have here. 1, 2. So this is 12. Is it more important to know that this person in his or her teens, or that their age finished by 2? Think about this person who's 32. Is that more important to know this person is in his 30s than to know his age finished by 2? So we see that the first number of these observations seems the most important one. This is the stem. Therefore, the stem in this case will be 1, 2, 3 for each of the number. Even if there's nobody in their 70s, I still have to put 7, because a stem is a list, a consecutive increasing integer. Even if there are no observations for 7, I still need to put it there. And then I know those who start with 1. This is 12. So 1 corresponds to the stem, and the leaf will be 2. 16, 1 and 6. 17, 1 and 7. Take, for example, 45. 4 is the stem here, and the leaf is 5. I put this stem in the same order as I have them. Very important. Condition: the stem will be a list of increasing consecutive integers. The leaf will also be increasing order. If two numbers like 58 and 58, we have the same number, they share the same stem, but we still have to put them 8 and 8. There's nobody in the 70s, so we leave it empty. It gives me, again, something interesting, the shape of the distribution. Now I need to specify what is the stem unit. When I use 1, I don't mean it's just 1 unit, but this stem unit is worth a 10, and the leaf unit is worth a 1. how will I know that? And how will I use this? So 1 bar 2. 1 bar 2. This is the first observation. I can take it as 1 times the stem unit of 10 plus 2 times the leaf unit, which is 1. So 10 plus 2 is 12. I can take any of the number from the stem and leaf display and reconstitute the original data. Sometimes if the numbers in the sample have many observations, many digits, so it might become an approximation. So this is what we need to know about stem and leaf. Very simple, and it is something that we use when we want to have a quick look at the shape of a distribution. As the second part of this module now, we'll look at building frequency distribution, cumulative distribution, and their graphical representation. We'll look at this part now. First of all, what is a frequency distribution? It's when the numerical data are summarized in a table by creating classes that do not overlap. So everybody has a place, all the observations have a place in the data, and the data is of course arranged numerically ordered classes. It makes it easier. There's a list of steps to create a frequency distribution. First of all, let's have the data in increasing order. Second, let's find the range, which is the maximum minus the minimum, and we saw that before, easily done. And then we'll have to select the number of classes. Too few classes is not good. Too many classes is not good, so usually between 5 and 15, but it depends on the sample size. Knowing that, I compute the class intervals, the width. So I know how many classes that I want, and I have the range, so I simply divide and find the approximate width. Then I can identify the class boundaries. I try to have simple to use class boundaries. Get the midpoint. For each class, get the midpoint, take the upper limit minus the lower limit, divide by 2, and count the observation and assign them to each classes. Let us take an example. Let us build the frequency distribution of the ages of 20 randomly selected people who went to see a movie last Sunday this time at Cineplex Odeon. Of course, my data set here needs to be rearranged, so I need it in increasing order. I can easily find the range, right? The maximum is 58 minus 12 is 46. How many classes will I use? Are you tempted to use 7, 8, or 9, or 10? Well, when I see a number like that, 46, not far from 50, it makes me think that 5 classes would be good. You do it, I do it, we might have a different number of classes. Of course, when I have small sample, it's going to be a big impact. The class width, I have the range, number of classes, 46 divided by 5, 9.2. I don't want to keep a width of 9.2, not easy, doesn't look good, so I will round it to 10. I like to have nice class boundaries, so from 10 to 20, 30, 40, 50, and 60. And that seems to be a good plan. Here are my data. Now I have my class intervals. Here are my classes. The notation I've used here show this is a closed bracket, that means 10 is included in the interval, and 20, you see the bracket is open, 10, 20 here is not included. I could write this class goes from 10 to less than 20, excluding 20 because 20 is in the other interval here. All I need to know now is identify how many observations are between 10 and less than 20. 1, 2, and 3. I have 3 observations. So this is my frequency. And the total is 20. It is easy to identify the midpoint between 10 and 20. The midpoint is 15, 25, 35, 45, and 55. I'd like also to identify the relative frequency. Relative frequency, we saw that before. 3 divided by the total, 20. That's 0.15. 6 divided by the total, 20, which is 0.3. Now I have a relative frequency. The relative frequency will add up to 1. I can ask also for the percentage frequency, and 0.15 is 15% or 30% or 25%. I have all the information required now. Whether I use a frequency distribution, a relative frequency or percentage frequency, it gives me the same information, and the shape of the distribution will be the same. So let's look a little bit more at the properties of frequency distribution. We saw it condensed raw data into a more useful form. I don't need to have a list of long data set. If I have them into classes, it makes it quite easy, and it's a quick visual interpretation. So it determines the major characteristic of the data, and it allows me to see a little bit about the shape. But keep in mind different class boundaries. If I use 5 and you use 6, the look will be different if I have a small data set. If I have a large data set, the impact of the selection of class boundary is greatly reduced. It's not completely gone, but it's reduced. And now these very nice tables, I need to put them into some good chart, and they're called histogram. That's the most popular one. So it's a kind of a vertical bar chart, and which is a histogram where there is no gap between adjacent bars. So we make sure we have no gaps. In the Pareto, I needed to create the gaps because we had categorical data. With my numerical data, I don't need that. The class boundaries and the class midpoint are shown on the horizontal axis, and the vertical can be frequency, relative frequency, or percentage, and the height corresponds to those numbers. The histogram provides the information about the shape of the distribution. If I have a lack of symmetry, symmetry would be in the center. You will have like a mirror, and what happened before the number and what happened after should look the same. So when it's not symmetrical, we call them it is skewed. So this is a property about the shape of the distribution. For example, if I look at panel C, this is a symmetrical distribution. I can see from the middle, everything is the same on either side. If I look at panel A, I can see that there is a tail. There are smaller and smaller and smaller. So there is a longer tail on the left. So we say it is skewed to the left. Panel B, I have a tail on the right. So I'll say it is skewed to the right. Panel D, the tail on the right is even longer. We say it's highly skewed to the right. This is just an interpretation. So the histogram allows me to make these small conclusions. So let us construct the frequency histogram for distribution of age of these 20 randomly people who went to see a movie last Sunday afternoon. I have already defined my frequency table. So I'll do a frequency histogram. So I will use my classes and my frequency, and we'll have something like that. You note there is no overlap and there's no gap, and I have identified on each one the frequency. I can also build the frequency based on percentage. So here, instead of having the frequency, I have the percentage. Another representation for that would be the frequency polygon. The frequency polygon is taking the midpoint of each class, and connecting them at the level of their percentage. So we have here the percentages here. So at the midpoint of the first class, which is 15, so the frequency is 15%. At the midpoint of the second class, which is 25, we saw this midpoint, and the percentage frequency is 30%. Here we go, 35 all the way to 25%. It is possible to create an additional class which will be between 0 and 10, although there's no observations there, and of course the frequency would be 0. So we could create an extension of this point all the way to 5, and the same thing all the way to 65. But the main information is given here. Why do we bother with frequency polygon? Is that I can do some comparison. Here we were trying to compare percentage polygon for the meal cost at city and suburban restaurant. So if I look at the red dashed line, we're considering suburban restaurant. And we say for meals costing $35, and the frequency is almost 35%. In the city, meals of $35, it's only at 20%. So there is a good difference between the prices, the cost of the meal, between city and suburban. I have similar thing when I compare the growth value and the value of the fund. Same thing, we see that the 1 year return percentage for the blue line, the peak for the growth fund and the value of the fund is not at the same level. Let us build now what we call the cumulative frequency polygon, or the ogive. The ogive will be based on a cumulative frequency. I don't have the cumulative frequency in this case here, so let us build it at the class interval. So I look at my class limit 10, 20, 30, 40, 60, 50 and 60. Now, this is how we build it. How many observations are less than 10? 0. How many observations are less than 20? 3. Basically, it's those between 10 and 20. How many observations are less than 30? 3 plus 6, 9. How many observations are less than 40? So it's 3 plus 6 plus 5. 14. And so on. So I have here a cumulative frequency. I can build a cumulative relative frequency. As we've done before, we'll divide everything by 20. 3 over 20. And we have here the same thing. So my classes are there. 3 over 20 gives me 0.15. 9 over 45, and so on. And we also have the cumulative relative frequency by taking the percentages. So let us build from that this ogive. So where do we find this? Here is a table that we will be using. This class, those are my class limit and the cumulative relative frequency. At the class limit of 10, I have 0. The class limit of 20, I am at 15%. So here it is 15%. At 30, we are here at 45%. And so on. At 40, we are at 70, and so on. This is a cumulative frequency. What is the use of that? If I want to answer this question, approximate the age exceeded by 40% of the people. It is a cumulative. It tells me less than. So if it is exceeded by 40%, it will be less 60%. So I identify on this ogive where is 60%. It's about here. And I go estimate it on the horizontal line, about 30 years of age. So I can see that the age exceeded by 40% of the people is about 38 years of age. This is a way to do an interpolation between the data. The ogive is frequently used, but it's usually called the cumulative frequency polygon. If I have two numerical variables, now 2 at a time to study, and they're numerical, so very often what we will use is the scatter plot, and it pairs the observation. One variable is measured on the vertical and one on the horizontal. So and then we try to look at the possible relationship between the two variables. Suppose here we have the scatter plot of the house price in $1,000 on the living space. So I'm trying to understand the price of the house based on the living space. First observation tells me that a house of 1,400 square feet is priced at $245,000. So we want to see this in a graph, and this is the scatter plot. What does the scatter plot tell me? It shows something that I have expected, that as the price of the house, as the living space increase, the price will increase. Somehow, I could build a line through the data. Oh, this line is called a trend line. So when we have two numerical set of observation, we use a scatter plot to give us an approximate shape of the distribution. If I have two numerical variables, but one of them is a time series, it's over time. So we measure we put on the horizontal axis time, and the other numerical variable will be vertical. For example, the number of cheating cases has been recorded from 2005 to 2013. So we want to plot this time series and identify any pattern over time. Of course, we put together all kinds of measures, so we hope that we will not have cases of cheating in the future. So if we put that, my variable here on the horizontal correspond to the years. On the vertical are the dots that here. So we have in 2005, which is here, I have 43 cases. In 2006, I have 54 cases, and so on. I can definitely see there seems to be an increasing trend in the cheating cases. We have to be careful. At some point in time, something might have happened in 2011 and so on. There seems to be a decrease. But when we study a linear trend, so we might find this is the kind of equation that we have here. But this we will see that later in the class when we look at simple regression and multiple regression. And now we will go to Excel and see how we can work these things out and get the best representation for our data. Here is the data on the Sunday attendance, and I brought it into Excel. There are many different programs that can be used to create beautiful histograms, so Excel might not be the best one for this. But since we are using Excel now, I will show you two different ways you can get an Excel histogram. So first, let us block this. So there is first of all the option to go to recommended graphs. Now I don't see it, so I'll go to all the charts, and here we find the histogram. The way Excel does it for us, it creates the divisions, it creates the class. So 12 to 28, 28 to 24, 44, 44 to 60. That might not be the graphs that we want. So this histogram is not the best. So let us look at when we do it ourselves and specify the class limit. Then I have to create what we will call the bins, which is the class limit. We said we want to go to 10, to 20, to 30, to 40, 50, and 60. This is the information that I need to run this in Excel. Therefore, I will say Insert. Instead, I go to Data. Data Analysis, and here is the option to use the histogram. So I'll do for histogram. It will ask me the range of my observation, so A1 to A21, the range of the bins, that's the way they're called. I use label and the chart option. This is what we find. Now let me enlarge it a little bit. The chart that we have looks very much like a bar chart, although it's called a histogram. So first of all, let me format this data series. I want to remove the gap. We should not have a gap when we use a histogram. The next thing we will do is to look at the bins. I don't want the bins to be called this way. So I don't want the bins to be called like that. So I will change that and put this. So my first bin, I will leave it with no title. This one is from 10 to 20. The next one is 20 to 30. 30 to 40. that will make my graph look much better. And here 50 to 60. Et voila. I will remove the more also. Now I have a histogram. It starts to look like what we want. The bins here, I will call that attendance. And these are the frequency. I can modify that. So this is how we can get a histogram in Excel. As we said, we can change the color, we can create something more beautiful, but for now, this is what we have, and it covers the need for this histogram. The next part is, let us look at this. Now we would like to have a frequency polygon or a relative frequency polygon. We know that to do that, the observations will need the midpoint. So let's start with the midpoint and the relative frequency. I need to insert a chart, and it's usually going to see it from the beginning, and here it is. So the chart that will be included for us here, you will have on the horizontal axis the midpoint, and here it will be given at the relative frequency. So this is called a relative frequency polygon. I could extend from the midpoint of the first class to an imaginary midpoint for a previous class that does not exist, but we will go to 0. So that's a way we can do that for the percentage also. The other option that we wanted is to build what we call the ogive. The ogive is the cumulative relative frequency. Similar approach, I will use my data here, and I will also ask to insert a recommended chart, and it will come quite easily with this one. This is the cumulative relative frequency. This is my ogive. At 10 is 0, and so on, it is increasing. And it will end at 1 or at 100%. So this is a way to get the ogive and to try to estimate proportion between the numbers. As we say, we can change the colors, we can change the titles, everything can be done. And now it is time to do a review test. So I encourage you to solve the problem with your calculator or with Excel. So it's good to be familiarized with both options. So I hope you enjoyed the module, and see you next time. Bye.